So as far as temperature is concerned, yes, the temperature can make a reaction go faster or go slower, and temperature can actually alter uh, the rate of reaction, right? So let's study the effect starting from the next page. Now, before I go with the next kind of process, I would really like to actually compare it with the previous one. So let's go a couple of pages back. Let's discuss a certain set of points. Now, in the very first experiment, you saw that we were actually talking about loss in mass. I hope you understand that we specifically picked an experiment that produced a gas as one of its products. We allowed the gas to escape our utensil specifically, which actually decreased the mass from a starting value to a final value during the course of the experiment. We noted it over time, and then we drew a graph about it. Now, moving on, this specific experiment is commonly considered as loss in mass experiment. Now, moving on, yesterday we studied another experiment after this one, which was slightly different. We never let the gas escape the reaction, though we certainly picked a reaction which produced a gas as a product, but instead of letting that gas out to the atmosphere, we actually collected the gas in a gas syringe. Now, this is actually collection of gas. So this one is commonly known as collection of gas experiment. Again, we noted against time and we plotted a graph for it, all right? But this time, when we're about to study temperature as the third factor, we're not going to go with any reaction that actually produces a gas which we may let go towards the environment, open environment, or which we may actually push into a gas syringe and collect it. Instead, we're going to go for a very different kind of experiment. This kind of experiment involves formation of a precipitate. Now, I hope you remember back from chapter number 5 that precipitate is the formation of a solid in a reaction, an insoluble solid. Of course, if the solid is insoluble, it's going to settle down at the bottom of the utensil we are working in. If that's a beaker or that's a glass, it's going to sink down to the bottom of it and settle down over there. Now, the reaction you clearly see, sodium thiosulfate is reacting with hydrochloric acid. There are 4 different products, and out of the product, which has a safe symbol of S, is the solid that we are about to form. And that solid is insoluble in water, so it's going to sink down to settle at the bottom of the utensil we are working in. And as you can see the diagram at the bottom of page number 86, he has actually shown you a diagram and an actual result for it. And you see in the actual result, we perform it in a beaker. We actually took a piece of paper, we drew a cross sign at those pieces of paper, we put the beaker on top of that piece of paper. And after some time, when the reaction is complete, this is the initial step for the reaction. And for the final step of the reaction, you see that the precipitate has been settled down at the bottom, making the whole solution opaque, and we can't see through, so we can obviously not see the cross line below it. The same thing is shown over here in a proper elaborative diagram. So you start adding the dilute acid, you start adding timer, and you actually view the flask from above to see whether the cross line has disappeared or not. As soon as the cross line disappears, you're actually supposed to know that time. Now, of course, since we are about to prove some temperature changes in there, so we need to perform the experiment at different temperatures. For different temperatures, we'll have different readings, and we can plot a graph. There is an actual graph over here. So instead of discussing it for the experiment, let's discuss it from that actual graph. Now, I hope you can see we have 5 points over here for that graph. And I am going to intentionally extrapolate those points for our answers. So this is the first one. I hope I'm doing it right, because extrapolation for diagrams like these a little bit difficult. Sometimes I tend to lose the accuracy, but let's try our best and see what happens. So there you go with the fourth point. And finally, the fifth and last point. All right, so notice that in our first experiment, the temperature with degree Celsius units are on x-axis. The time for the cross line to disappear in seconds is on y-axis. For our very first experiment, let's say it was about 23 or 24 seconds. Let's say it was about 28 seconds. Let's say this one is about 34 seconds. Let's say this one is about 46 seconds. Let's say this one is about 58 seconds. Oh, my bad. Degree centigrade. These are all degree centigrade, not seconds. Okay, so 20 seconds. This one must be around 38 seconds. This one must be around, let's say, what, 66 seconds. This one must be around, let's say, what, 92 or 93 seconds, probably. This one is closer to 130 seconds. So that's, there you go. So at 23 degrees centigrade, we can finish the entire experiment in 130 seconds. If you increase the temperature, you see the time for the cross line to disappear in seconds is actually getting smaller, which means it has an inverse relationship. And that actually you can notice from a graph that has a decreasing trend. Though we are just discussing this graph in chemistry, but overall graphs are usually discussed in the subject of mathematics, or sometimes for the sake of understanding, since there are many graphs in physics, and you obviously start with the chapter of motion and you have some speed time and velocity time graphs or distance time graphs to face. So you do definitely get an idea about a decreasing trend graph, which this one is, and that tells you that both the quantities we're discussing have an inversely proportional relationship in between them. In this case, temperature and time. So as soon as you keep increasing the temperature, the lesser amount of time you require for the reaction to complete, in this case, for the cross line to disappear. Do you get the point?
Yes, sir.
Great. So this clearly tells us the idea, though I am over here for the sake of explanation, have been using the terms like directly proportional or inversely proportional, but the point, when you are about to make that point, remember in IGCSE, you never use the words proportional for this chapter of a rate of reaction to explain yourself. You are always supposed to go with the words of increase and decrease. Let's say if you're supposed to explain the expression I've just written, you're not supposed to write this expression over there. You're supposed to say and use the words like when temperature increases, the time decreases. So use the terms of increase and decrease in comparison or in relation to explain yourself for different factors affecting the rate of reaction.
Should I write a note on the book that says that I should use these specific words? Would that be a good approach?
Yeah, sure, go ahead. You can always take notes on the book, that's fine. But in this chapter, usually we don't ask you to not use some specific words, but for this chapter, I actually appreciate the students if their sentences are not just composed of proportional to, inversely proportional to, directly proportional to. No, drop these phrases. Use the words or the proper terms of increase and decrease for one factor in relation to another to give examiner a proper idea of your understanding about the question. All right. And yeah, it's a good approach for writing a few set of hints and tips of what to do and what not to do for a specific set of topics. Because do's and don'ts are something that are different for different topics. And I tend to tell the do's and don'ts, whatever required in a topic.
Okay, sir.
Okay, so now if we clear, I'm going to go back to the previous page. And since we are at at this point, I hope you'd quickly understand if I put it like this. So the pink portion on the top of the page, the important part, the rate of reaction increases for the temperature of the reaction mixture is increased. Okay, I would rather add something important to it. Actually, temperature, if I be exact, increases the average kinetic energy. Sorry, not like this, average kinetic energy of particles. And of course, by increasing the average kinetic energy of the particles, the rate of reaction or for the reaction mixture would definitely increase. Since now they can move faster, they can collide more fiercely, so of course, the rate of reaction would increase. So you also see he's using the same term in the book over here, but that's the only place in the book where he probably uses a directly proportional sign. But since the book was written a long time ago, I think the book was written and published back in 2016. So I suggest that we keep the changes that Cambridge is making towards the papers and their checking patterns in mind. So a graph of 1 over time against temperature would show how the rate of reaction increases with the rise in temperature. All right. So if we go for inverse of time graph, then instead of having a decreased graph, we would actually have an increased graph. Since we're directly discussing time and temperature, we're having this. If 1 over time over temperature should be taken, it would give us an increasing graph. That's what you can do to get an increasing trend of graph for the two quantities or two factors that have an inversely proportional relation between them. Remember, inversely proportional graphs usually turn up like this. So if you want a graph with an increasing trend, you should go for one of the quantities as inverse and other one as it is. Make sense?
Yes, sir.
All right. So this
So,
makes
sir,
sense.
it shouldn't be really smooth, the curve. It should be straight.
That really depends upon how the reaction proceeds. Okay, if you're asking that, let's go with it. Now, the reactions behave differently in different cases. Now, let's say for an increasing trend graph, let's talk about that one. Since we are at it, we should do the mathematical way. Now, what I'm about to tell you is more mathematical than it is chemical, but you should have an idea because we time to time discuss stuff quantitatively. We sometimes plot graphs about it. So it's important that you understand the point. Now, the increasing trend graph can be of three types. This kind of graph, this kind of graph, or this kind of graph. They're all increasing graphs, but they have different trends. Notice for the first one on the left, it increases with maximum numbers. It increases with maximum pace in the start of the reaction, but it still slowly settles down or becomes slower. This is what the first graph does. The graph in the exact center keeps on increasing throughout the time of the experiment or course of the entire experiment in a similar way. That's like a car moving with uniform velocity, all right? And uniform speed, I should say, not velocity. And the last one, the extreme one on the right, it should give you an idea that we are slower in the start, but we exponentially increase our pace at the end of the experiment, towards the end of the experiment. So this is an increasing trend graph. There can be three kinds of increasing trend graph. If I slightly change it, and let me clarify myself if I change it in this way. If we are supposed to go with a decreasing trend graph, so then everything would change in the same way. The decreasing trend graph can be of the same type like this, or maybe like this, or maybe a little bit like this. Now, the extreme one on the left tells you that we have the maximum pace of the decrease in the first few seconds or the starting part of the course of reaction, but then it slows down. The graph in the center tells you that it keeps on decreasing on a uniform pace. The graph on the extreme right gives you an idea that we are slower in our decrease in the start of the experiment, and towards the end of the experiment, the decrease was exponential. We decreased a lot in the last few seconds of the experiment as compared to what happened to the starting few seconds or the starting few portion of the experiment in terms of time. Make sense?
Yes.
Now, apart from these, what I've just shown you, we can have a static trend graph, right? A static trend graph is a graph in which you get a graph actually parallel to any one of the axes. The first graph is parallel to x-axis. The second graph on the right is parallel to y-axis. And at exact one point of time, you have the whole value, the whole raise, and for the rest of the experiment, you don't even get a raise for a specific temperature or specific time or whatever quantity you are measuring it. So you can have different types of graphs. And I tend to ask my students that whenever you are going to compare chemistry with maths and you're going to plot graphs, you should at least be familiar with different kind of graph that you might face in chemistry. And these 8 essential types actually give the student a necessary idea of what might happen in an experiment in increasing or decreasing trend graph, or maybe a straight line graph like these two. All right. So this is not exactly chemistry. This is more related to physics. This is much more related to math, since graphs are covered in math portion. But if you have some basic idea of graph, whether it's related to math or physics, or whenever we are plotting graphs in chemistry, it actually helps better for the student to understand the whole experiment or how the whole thing went. Right?
Yes, sir.
Which actually brings me to a point that we need to discuss. Let's find some empty space that we need to discuss about the gases. Okay, I added a couple of factors to the initial factor list that we started off with the 7.3 topic, rate of reaction, and there were 5 bullet points, 5 factors that book discussed. I intentionally added a couple of them, a couple more to it. I converted them from 5 to 7 factors. Now, if you remember, I added pressure volume for gaseous reactants as one of the factors, and the second one was time. Now, if I be exact, you have already studied time over here in terms of rate of reaction. Now you already understand for rate of reaction time are inversely proportional. If I be explaining this relationship again, let me clarify. For faster rate of reaction, you actually take less amount of time. And this exactly goes with the speed of car. If you're supposed to cover the same distance, the faster you're going to move, in lesser amount of time, you're supposed to cover that exact distance. Now, you may commute to school every day, right, on weekdays, and you exactly remember the route you take every time. Now, you know that if you're going to commute a little bit faster, you're going to have to spend lesser time for those whole commuting portion. And if you're going to go slower to commute toward from home to school, you're actually going to take a little bit more time. I'm not asking you to overspeed. I'm of course asking you to stay under your speed limits, be safe, but the relationship I'm comparing right now is between the speed of the process or the work you're doing and compared to what time you're going to take for it. All right? Don't ever take the meanings I'm asking you to overspeed. That's not what I'm asking. All right? Okay, coming back to it, there was a factor in which we discussed pressure volume as a factor for gaseous reactants. Now, let me clarify that for gaseous reactants, the volume actually acts as concentration for gases. All right.
Yes.
And since volume is directly proportional to number of moles of gas is going to be directly proportional to volume of gas.
Sir,
So
the volume would be 24, right? That has we previously discussed for gases.
that's molar volume, which means we're talking about 1 mole of a gas at room temperature and pressure. Molar volume has a very good specification for it. The quantity should be 1 mole, the temperature should be room temperature, the pressure should be room pressure. Then the value would be 24 decimeter cube. And yes, you're right about that. And that goes for any gas on the planet. No matter which gas you name, the volume occupied for 1 mole of that gas at room temperature and pressure would be 24 decimeter cube. So since we're talking about this, and this actually goes for concentration, okay. So I think actually it's better to relate these two. Take this one out. So number of moles of gas is like concentration of gas. Okay. If you understand this point, I hope you clearly understand the more moles of gas we're going to use, the higher concentration of gas we'll have. And the higher concentration we have, now we have already studied concentration of a reactant. Higher the concentration of a reactant, faster would be the rate of reaction. Which means, if I rewrite it, more number of moles of gas, higher concentration of gas, and of course, faster rate of reaction. Make sense? So that's what we
Sure.
actually discussed for gases. Were you about to ask something?
Yeah, no, sir.
Okay, good. So if this makes sense, you would understand that I am simply talking about putting more number of moles in a specific place or more number of molecules of a gas in a specific place for higher concentration. Imagine if the gas has 1 mole in a specific place, and that 1 mole would have certain number of molecules uh, covered in that place. If I convert that into 2 moles, now I have doubled the volume, doubled the number of moles, sorry, my bad. I've doubled the number of moles, and actually there are going to be more particles in that area. And if there are more particles in that area, of course, there are more chances of them to collide with one another, to be converted from reactants to products. That's how it works. The more the number of moles of gas in a given space, higher would be the concentration of gas and faster would be the rate of reaction because there are simply more molecules present. It's like I have more workers to do the same task. And if we have more workers, we can have a higher speed, right? I sometimes explain this to my students, but consider you have a specific amount of homework. Let's say you have a 10-page homework. If that homework has to be done by a single student, the student is supposed to do a 10-page homework alone. Now, if I actually divide that task in between 5 students, on an average, every student will be only doing a 2-page homework. Let's assume I divide that task among 10 students, then in an average, every student will have to do just 1 page of homework. So of course, you're going to speed up the whole process. Imagine the amount of time they're going to take to complete their task. So of course, the 10-page homework would require more time, as compared to a 2-page homework or even a single-page homework. Of course, faster rate of reaction. Make sense?
Yes, sir.
The point I'm trying to make is that apart from whatever we are learning, if you're going to compare it with your daily life examples, you actually take those molecules and you replace them with something else. You just think about your homework or you think about any other task, you might be able to come up with a very logical answer for your work. So at any point, if you are sitting in the exam and you get stuck, you don't understand about molecules, and it is giving you a little bit of a hard time, replace it with something easier to think of to get a more logical answer. But try to be fair with your replacements and do not pair it with something illogical. Otherwise, you're gonna go more astray, right? So let's clear all of this up. Move on. Next up is 7.3 catalyst. Now, we all understand from the basic definition of catalyst we have studied in the previous classes. Everybody knows catalysts are used to speed up the reactions, but we are definitely going to explain you the working of catalyst in a much deeper understanding at this point. So let's start with the basics. Let's start with an example and move on for a further explanation. Of course, we're going to go towards the definition too, but first an example. And this example is considered very important in O-levels, IGCSE, and Cambridge, since this is one of the examples which can uh, be explained for all the purposes of catalysts we are supposed to achieve over here. The example is decomposition of hydrogen peroxide. Hydrogen peroxide is a colorless liquid. The formula is H2O2. It is a very reactive oxidizing agent. And this, when comes in contact with human, it has the capacity to change the color of your hair. So usually the hair dyes have this. It can actually bleach your hair white. So not all the hair colors consist of H2O2. So hydrogen peroxide decomposes to form water and oxygen as per the given reaction. We can perform this reaction in lab. Now the formation of oxygen is very slow at room temperature. We understand we're talking about a catalyst, and catalyst can speed up the reaction. And in this case, the specific catalyst we can use is the powdered manganese peroxide, MnO2, which is actually a black powder. And we're going to take a very small amount of it. As you can see, it's just 0.5 grams. And this is going to make the reaction go much faster. We're going to notice that the black powder, MnO2, do not disappear through the reaction. When we're done with the whole reaction, we can filter this solid, get it dried at the end of the reaction, and actually calculate its mass initially at the start of the experiment. And finally, at the start of the experiment, we calculated it to be 0.5 grams. If at the end of the experiment, we have the same amount and it is 0.5 grams, it means catalyst is something that we get by the end of the reaction in the same mass, which is actually great. This is something you might have studied along with the definition of the catalyst in the previous classes. Okay, so moving on, if the amount of MnO2 powder is added and doubled for a reaction, the rate of reaction increases. Keep this important point in mind that the amount of catalyst, if increased, uh, obviously it's going to increase the rate of reaction. But I would definitely say this goes in optimal conditions, which means up to a certain extent, the rate of reaction would increase with the increase in the amount of catalyst. But after that, it would stop. That's why it's optimal. At one point, the increase in the amount of the catalyst will not increase the rate of reaction. And at that point, you shouldn't be using any more catalyst because it won't bring a difference. Now, catalyst is mostly used in the powder form. This means increasing the surface area. And you definitely understand that in case of solids, surface area is very important and can increase the rate of reaction. This is something that we started off with when we started the factors for rate of reaction. So that it does not just applies to solid reactant, that also applies to solid catalysts, right? So take a look at this. We started off with an experiment. We have an hydrogen peroxide solution. We added manganese peroxide to it, 0.5 grams. We have the collection of gas experiment. Since you're done with this experiment, you already know that we are going to produce a gas as a part of product. And that gas would be collected in a gas syringe. The plunger is going to move outwards. We have the measurements on the gas syringe, which would tell us that how much is the amount of the product, gaseous product that we collected. Now, we are going to note all of this against time in order to note the rate of reaction. What we can do to prove that we will get the same amount of the catalyst back at the end of the reaction is that we can filter the whole product. We'll get water, oxygen was already collected in a gas syringe, and we can get the black powder on the top of the filter paper. Dry it up, wait, and this should be exactly equal to 0.5 grams. No more, no less. If the weight is coming out to be more than 0.5, it's not completely dry. If it's less than 0.5, there must be a human error towards that. It might be a systemic error, I don't know, but there must be an error, right? So moving on, if we plot a graph of time on x-axis in seconds and volume of oxygen as a gas collected in cubic centimeter on y-axis, you'd understand for this specific two sets of experiments, G and F. In F, we have 0.5 grams of manganese 4-oxide black powder. And in G, we have double of that amount, 1 grams of manganese 4-oxide black powder. And you'd notice they have a different rate of reaction. Of course, a more steeper curve. So I was saying in experiment F, we have 0.5 grams of our catalyst, manganese peroxide, and in G, we have double the amount. And we can see that the rate of reaction definitely increased for G, and we have more steeper curve for G than we have for F. Apart from the fact that increasing the mass of the catalyst increases the rate of reaction, remember, this goes to an optimal point. It goes to a certain extent. You can't just keep on increasing the mass of the catalyst, and you can use tons of catalyst to proceed with the reaction in a matter of seconds. No, it doesn't work that way. Keep in mind that up to a certain extent in increasing the amount of the catalyst would the rate of reaction increase, and after that, it won't have any effect like that. So that's why we keep using the word optimal effect, or to an optimum it works, all right? Apart from that, remember that we prefer using a powdered catalyst as compared to smaller chips or bigger lumps or bigger pieces. So a powdered catalyst having a larger surface area, though having a smaller particle size, would give us a better, actually better help towards increased rate of reaction. Now, we already do understand that we'll get the same amount of the catalyst by the end of the reaction. So let's get towards the definition of the catalyst, the final thing. And this definition, it's important that you understand the definition and use the same words or phrases to explain yourself. If you change the words, if you try to omit a word out of it, the definition might not explain the same thing which it is supposed to and would be considered as incorrect. The definition of catalyst has been asked in previous exams, but not the recent ones. I haven't seen the definition of catalyst to be a part of any questions in the theory paper in past 5 or 6 years. But if we go a decade back or more, yeah, you would definitely see the definition of catalyst. But again, it's important that a substance that increases the rate of a chemical reaction, but itself remains chemically unchanged by the end of the reaction. Now, this word specific term is chemically unchanged, which means it will not change its chemical identity, but which also means it may physically change. And yeah, that happens. That happens a lot of time when you feed a solid catalyst at the start of the reaction, and the catalyst tends to melt or boil through the course of reaction, or you add a complete piece of catalyst, a big piece of catalyst at the start of the reaction, and by the end of the reaction, you get powdered form of the catalyst. So yeah, it may physically change. It may melt, it may boil, it may be converted from a large lump to powder or from a powdered back to a large lump. So anything can happen to the catalyst physically, but the chemical identity of the catalyst will not change. So by the end of the reaction, you'll have the same amount of the catalyst with the same chemical identity. Now, apart from that, a couple of more important things. Many catalysts work by providing a surface for other molecules or atoms to react. This is commonly known as rendering its surface. By rendering its surface, it's exactly similar to what happens to frying of an egg on a frying pan. Now, in our breakfast, we commonly have a fried egg. How do we fry that egg? No, we usually don't throw the egg into the fire. That would fry it. That would actually burn it. What do? We render a metal surface or any surface for that matter. We have different surfaces for frying up an egg. So we render a surface. That surface actually keeps the egg and the fire apart from one another and just let the heat pass through for the reaction to occur. So on that surface, the egg is properly fried, and we can enjoy the egg afterwards, right? So the surface of the metal and the surface of the catalyst work in a very similar way almost. Though I'm not talking about chemically, but of course, the surface can be rendered for the reaction to occur. The molecules and the atoms would come to the surface, react on that surface. The reactions would be converted into products and then leave the surface again. Just like an egg comes to the surface of frying pan, gets fried, and then leaves that surface, right? So that's one of the most common way how catalysts work. Goes good for many solid catalysts. However, there are other complex ways a catalyst work. Thus, it is not wrong to say the catalysts do not take part in a reaction. Some do, but by the end of the reaction, same amount of the catalyst and with the same chemical identity without being chemically changed, that's what you're going to get. All right. So I hope this completely explains the part of the definition that has the phrase chemically unchanged by the end of the reaction. Now, some other examples of catalysts. We have some very important catalyst examples in our book. Throughout the book, we are about to study a lot of processes which are going to be important industrially or otherwise, and catalysts are used for those processes. Now, since catalysts...
Sir, I have a question with catalyst. Um, sir, so they do mix up, right? But they don't react with
they do
the
mix up,
substance.
they do react,
Or
but by the end of the reaction, the identity does not change and we get the same amount. That's the best part about the catalyst. A catalyst is more like a helper who is not consumed during the reaction. We get the same mass by the end of it, whose identity is not changed during the reaction. We get the same chemical identity by the end of the reaction. So yeah, they do take part. They may change during the course of the reaction, but by the end of the reaction, we get the same amount with the same identity.
sir, the question is, sir, like, do they mix up, such as like we
Yeah, they
mix
do.
up salt with water?
Yeah, they do,
Oh, okay.
definitely. That's why
The perception
actually,
that they would be like oil.
I am going with with a much deeper meaning to it. You're just talking about whether they mix or they don't. Yeah, they do mix. I'm also saying that sometimes they do take part in the reaction in such a way that their identity changes a little bit, but by the end of the reaction, their identity comes to original. So yeah, sometimes they do dissolve, they do mix, they do change their identity during the course of the reaction, but by the end of the reaction, they would be the same. And that's the best part about it. During the reaction, they do whatever is required to change the rate of reaction, to increase it, do better, but by the end of the reaction, same mass, same chemical identity. And that's actually great, which means, why is that great? And that's written right over here in these lines. If they're unchanged by the end of the reaction, they can be reused over and over again. So industry, they're very important. We increase the rate of reaction when we keep on reusing them. And we actually use catalysts to make everything from polythene, plastics, painkillers, fertilizers, fabrics, name a thing. Industry tends to use catalysts for many important chemical processes. Because if the catalyst does not exist, the chemical processes would be very slow. If I don't take the example of chemical processes, instead, I take an example of a biochemical process. Let's talk about human digestion. Digestion is a biochemical process, right? You might have already studied it in biology. Now, in that process, if the catalyst did not exist, that process would have been very slow. It would have taken too many hours or even days to digest that food. If the catalyst did not exist, the proteins we love to enjoy and digest, or the fats we love to enjoy and digest, would not digest so easily. So they actually speed up the reaction, and the reaction proceeds at a reasonable rate. It becomes economic, it becomes good, it becomes a little bit faster. Let's discuss the exact industrial processes with the catalyst in example, which we are going to discuss right in your book, in your IGCSE course. So definitely Haber's process, ammonia manufacturing, the catalyst is going to be iron. For sulfuric acid manufacturing, we're talking about H2SO4 over here. We were talking about NH3 over here, that is contact process. We're going to use vanadium 5 oxide, the formula for which is V2O5. These examples which I'm quoting will come as a part of chapter 7 or chapter 9 or 10 or 11. These are all present in your book. This one is 7 and 9. This one is also 7 and 9, since most of the industry is discussed in chapter 9. Then margarine production, hydrogenation of fats, nickel. We're going to discuss it in chapter number 10. Nitric acid manufacture, oxidation of ammonia with platinum rhodium gauze. We are going to take a similar example over here, but this would be discussed in chapter 9. Fermentation of sugars for the alcoholic industry, drinks industry, the alcohol that is commonly used for drinking purposes, enzymes as in yeast, chapter number 10, since we're going to discuss alcohols in chapter 10, the conversion of methanol to hydrocarbons by using a mixture of catalysts, the industrial name to which is zeolite ZSM 5, that is actually coded name, and that's going to be chapter 11. So we are going to discuss many different catalysts at different points of discussing the industry. For example, the diagram given below actually discusses the catalytic converters that we put in cars. Now, it's a very common thing in cars. Any or every car that has a catalytic converter would be written on the rear or the front windshield that it has catalytic converter. Now, what does a catalytic converter do? It is actually fitted into the car exhaust system. And exhaust stream actually consists of gases which are toxic. Carbon monoxide, poisonous gas, can kill. Nitrogen monoxide, not exactly poisonous, but definitely pollutant, can pollute the environment. They're unburnt hydrocarbons. They can also pollute the environment. All of these gases can either be toxic or can cause pollution. So what do? We actually put a piece of this catalyst. This is a platinum rhodium gauze, which has a kind of like a beehive type of structure with many small pierced holes in it. And this converts every either toxic or pollutant gas into a much less harmless product. For example, carbon monoxide, nitrogen monoxide, hydrocarbons are all either toxic or pollutant. They're converted into oxygen, carbon dioxide, nitrogen, water, the gases that are usually a part of our atmosphere. So I hope this gives you the idea that a toxic gas, with the help of this catalyst, is converted into less harmful gases. Oxygen is not harmful at all. Nitrogen is not harmful at all. Carbon dioxide, though, is a greenhouse gas, but that's even a better choice as compared to carbon monoxide or nitrogen monoxide. These are the reactions which you're supposed to memorize for catalytic converters, and they have been a part of past papers. Yes, you were asking something?
Sir, these catalytic converters contain catalyst, right, sir? That you use to
This itself
convert.
is the catalyst. This structure, this beehive kind of structure with platinum rhodium gauze is itself the catalyst. And that's the kind of catalyst which renders its surface for the reaction for these gases to occur.
Sir, I'm kind of confused at a point because if I remember correctly, you have to change these converters every year or every 2 years because if we don't, then the gases that are produced are really dark from at the end of the exhaust, I suppose, in cars. So your previous
Very
statement
good
was,
point.
sir, that catalysts always stay, the same. They don't get reacted. So, sir, isn't this kind of contradicting the point
No, it
that
is a
because we have to
very
replace
good
it?
question. And let me answer your question by going through the stuff over here. Now, yes, you're right, but that doesn't exactly mean the catalyst reacts. Now, the problem, because of which we are doing this, is that catalytic converter actually removes fluting oxides that speeds up the reaction. We have a honeycombed surface, and we give it a considerably good surface area for the reaction to occur. This has thin coating of rhodium and platinum catalyst on a solid honeycomb surface. This has many tiny pores, which provides large surface area. Coming to your point, now this can only be used with unleaded petrol. Unleaded means the petrol that does not consist this specific element, which has the name lead. Now, the presence of lead acts like a poison to the catalyst. Why? It actually clogs the points. Have you seen this honeycomb surface with very small holes? These holes are clogged if you use even a little bit of lead. And since lead was commonly used in gasoline before, although we don't use it anymore, but lead was previously commonly used, so it can clog it. Apart from lead, there are some pollutants in our environment whose presence, if increases a specific amount, can clog this. So yeah, we need to rechange it after a couple of years or after the specification mentioned on the catalytic converter. That is because impurities get deposited on the catalyst surface. The converter eventually needs replacing after a specific number of years. For different converters, that is a different requirement in years. All right. I hope that answers your question.
Yes, sir.
Okay, great. All right. Let's